Tell me when you guys are ready. You guys ready? Okay. Yeah? Okay, welcome back, everybody. That's really big. But today we're gonna move on beyond the pendulum. Although honestly, I'm going to return to the pendulum and other low-dimensional systems every time I can throughout the class. As we start introducing more complicated algorithms, I want to make sure we can draw them when possible and understand what they do for the really simple systems. But going forward, I want to understand how to control systems that are more complicated than the pendulum. Okay, so I feel like we've covered some of the preliminaries here. I'm going to reuse some of the ideas we've talked about before. In the very first lecture, I told you about the manipulator equations. We'll use those again today as a general form of the equations of motion for these robots. We talked about feedback linearization. And then we started talking about optimal control as a maybe better way to program these systems. And in particular, we talked about value iteration as the numerical algorithm of choice so far for the simple systems. And the question for today is, can we go farther with it? How far can we go with value iteration? So I want to start introducing to you some of the canonical underactuated systems. So there's a bunch of, if you talk about underactuated systems, there's a bunch of systems that immediately come to mind. As if you Google underactuated systems, you'll see papers, a lot of them by Mark Spong, or just a few people out there that have done some of the seminal work here on the so-called model underactuated systems, or the canonical. Probably the most famous of them is the cart pull system. Some people call it the inverted pendulum, but for obvious reasons, since we've talked about a pendulum by itself without being on a cart, I'm going to call this one the cart pull system to distinguish it. And we'll do this one in a little bit of detail today. There's another one that we're going to talk about today, which is the acrobat. There's a slew of more that are sort of in that class. So there's something called the Pendubot, the Furuta pendulum you might have heard of. The reaction wheel pendulum. These are all sort of pendulum type examples that are cool and actually are good fodder for class projects. There's one called the ball and beam. And then there are a few that look more like vehicles. For instance, what used to be called the planar VTOL system. Well, these days we'll think of it as a quadrotor. Or a full quadrotor is a good example too. There are hovercraft models, bicycle models. Which, by the way, are some of the most common models used in autonomous driving, right? You don't actually have to get too complicated to capture a lot of the interesting dynamics of not hitting somebody on the road. Okay, so there's a bunch of these, and I'll pick a few of them and go into some detail and just show you that we can handle a handful of them, and trust me that the same tools will basically work for all of these. Okay, so the Acrobat. Let's start with the Acrobat. I can show you first what it is. Well, let me draw it just so you know what you're about to see here. So now we're graduating from a one-link pendulum to a two-link pendulum. Okay, but unlike the version I did in the very first lecture, I'm going to give you a motor here, but I'm not going to have a motor here. So this is the torque at the elbow. Yes, but the torque here is equal to 0. There's no motor applied there. Okay, so the idea is that you have to somehow do something clever at your elbow in order to swing up and balance at the top. And it's called an acrobat because it's a bit like an acrobat on a high bar, where if you're holding a high bar, you probably aren't going to swing up and balance by yourself just using whatever you have available at the wrist. You have to do something more at the waist. Now, an acrobat an acrobat has more than two links, but roughly speaking, you're not generating torque right up here. You're generating it with something, either your shoulders or your hips to do the same thing. And acrobats can do amazing things, and we should expect the same out of this robot. So you can build an acrobat, and it's fun to do that. We've, of course, done that in the lab. This is roughly what it looks like. Okay. For reasons we'll understand better in a little bit, it's actually got a huge lead slug at the end of it, right? So don't go too close to it. We talk about the plane of the acrobat, and you should not walk in the plane of the acrobat, especially after I threw the pendulum across the room. Okay, but you can see it gets up and balances despite having no motor at the shoulder. Okay, and we'll understand that today. You can also ask the question about what does optimal control look like for the acrobat, and we should expect that if we solve it well, then you should be able to do pretty snappy things, right? This is a swing up designed with an optimal controller to just go right to the top. And we should be able to do that kind of thing too. Maybe not today, but very soon. This is the cart pole system, which is very similar. It's the famous sort of inverted pendulum. Ignore the particular algorithm talked about here, but just to show what we're talking about with a cart pole. You have control of the force on the base, but you have, again, a passive joint here, and your goal is to swing up and balance it at the top, right? It's kind of extra bonus if you can handle a limited track, because that's more practical for lab, but it imposes some hard constraints.
So there's no...
Correct. So the cart pole you apply a force here on the cart, but you have no torque. It's just a passive joint there, apart from friction. Right? Okay, and for bonus points, you might have X limits. That does make it harder. Okay. I will presume that you know what a quadrotor is. We'll show videos of that when it's time. Okay, so the question we've got to ask ourselves first is, to what extent do we already know how to solve these problems? Let's dig in and look a little bit at what the dynamics look like for the systems, right? The equations of motion for both of these The full version of them are in the notes, but what we're going to be able to do is leverage the fact that they all have this characteristic form in the manipulator equations, right? Oops. For the acrobat, we're going to choose Q is going to be, just call it theta 1, theta 2, theta shoulder, theta elbow, whichever your preference, okay? Our, you could call it shoulder, elbow, okay? Our U is just going to be a scalar, which is the torque at the elbow. That means B matrix is going to be 0, 1. It's underactuated, okay? Surprise. And to keep it interesting or reasonable, we're going to put a torque limit on there. You sort of have to do that, otherwise you can make things happen that shouldn't, that look physically arealistic. Which, by the way, is what happens in all the videos of Deep RL, right? They forget this part, and then things look ridiculous, and that's why. But good luck running that on a real robot. You need torque limits, and it reduces the class of possible solutions considerably. For the cart pole, similar. Our choice of Q is going to be the x position of the cart and the theta of the pendulum. For pole. This time our U is going to be the force on the cart. B in this case ends up being a direct force on the x variable, but it's still low rank, still underactuated, right? I want to put a force limit on here too, again. And for bonus points, we can say you're on a track that ends, right? Or I could even, given having written this, I could say specifically that the x on the cart is less than the x max. And the task for both of them is to swing up and balance, okay? So the question is, do we already know how to do it? I think the answer is sort of yes, okay? So value iteration could work for this. It's actually kind of fun, it would be fun for me to have you try, but I'm not going to do it here because it's actually not a satisfying solution. The amount of grid points you need to get a good solution is ridiculous. Okay, it's 4 dimensions, so of course you have the fact that you're tiling in 4 dimensions. That's already one factor. So, you know, if I have 10 bins in 4 dimensions, 10 to the 4th, but you need a lot more than 10. It's the resolution that you need is surprisingly fine. And you see that even the small errors that we saw in the double integrator example, these sort of get amplified in higher dimensions. And if you even want to, in the vicinity of the upright, try to stabilize, you will be shocked at how much resolution you need, to the point where I don't consider it a satisfying solution to the problem. This is right around the boundary of what you could do it, but there's better tools, okay? And it's partly because of the need for resolution, and that's sort of related to the numerics, okay? In fact, if I were to, as I decrease my torque limit, those numerics are going to get more challenging, meaning that, you know, your system, the difference between your highest and lowest actuators are going to be smaller. It's going to land in more subtle parts. You know, it's going to require finer resolution to distinguish the long-term implications of that, and it's just going to drive the requirements up in terms of resolution. So, especially as the torque limits go down, you will see value iteration fail for numerical reasons, suggesting that there is no solution that has finite cost, but really it's just because the resolution's not high enough. It's a numerical error. What would value iteration look like if it said that, right? The cost to go would just get higher and higher and higher on every iteration. It would never converge. That would be the case. So if I was setting a cost to try to get to the top, right, and it thought it couldn't achieve the top, then the cost at the other states is just going to go up and go up and go up, and it'll never converge, right? If it thinks it can converge, then if it thinks it can get to the top, then it'll find a way to get to zero cost, and everything will converge. Okay. But we did give you one version of dynamic programming where we can do pretty arbitrary scales, and that was in the case of linear systems. The linear quadratic regulator that I did more with equations at the end of class, but I want to build up your intuition about it this time. And I showed you Atlas balancing. So there's a suggestion there that it should work for more complicated systems, and let's start by doing that. Okay. All right, so the immediate question you should ask yourself is that, well, LQR was for linear systems, and no, that's not a linear set of equations, so what do we do about that, right? We had x dot equals ax plus bu was our initial formulation, and we said that our cost was written in this form x transpose qx plus u transpose ru. Then it put out, we found out that the optimal solution was x transpose sx and u equals negative kx, and that we could get this from a numerical recipe, right? So how do we start? If we've got a nonlinear system, then how do we use this tool? Well, the first thing is we have to approximate it over some part of the state space as a linear system. And what I want to help you understand is how well that's going to work. And the answer, of course, is problem specific, but let's try to see it on some of these systems, okay? So how do I make a local approximation? Well, first I have to pick where in state space I'm going to approximate it. So let's call that some nominal configuration x0, u0. And then I can just take a Taylor expansion of the dynamics, right? So x dot is approximately equal to whatever it was at that operating point, plus the first order approximation. Where those partial derivatives are evaluated at the operating point. Okay. Let me summarize this, calling it x0 dot, right? It's what I did. It's the nominal velocity at that operating point. Let me call this matrix, which is A, this one B. And so what I have here is the equations x minus x0 dot equals A x minus x0 plus B u minus u0. So in order to make this into a linear system, we have to change variables, change coordinates. Into we think of it as the error coordinates, the coordinates relative to your operating point. X bar is now x minus x0, right? So x bar dot is x minus x0 dot. U bar equals u minus u0. But to be fair, this is, that's sort of a weird thing. If your coordinate system is changing over time, you'd like this to be, for it to think of it as a coordinate change, you'd want this to be 0. Otherwise, your coordinate system is moving, right? Okay? And then once I've done that, now I've achieved my goal of having actually a linear system, or a linear approximation of the system. So what does this wanting to be 0 mean? What's the implication of what you can pick for an operating point? Say it again? An equilibrium point. An equilibrium point of the original system, right? So, and that is a point x0, u0, if it's a fixed point of the system, right? So, for a quadrotor, for instance, a fixed point has non-zero thrust, right? Otherwise, you're going to be falling out of the sky. So, you might pick a nominal point. Actually, any x and y are going to be okay. Probably you want theta to be 0, but your torques need to be balanced in gravity in order for you to have a fixed point. So it doesn't have to be u equals 0. It's the total combination has to be a fixed point. Okay? So to what extent does that capture the dynamics, right? So we've been talking about, we've been drawing dynamics of nonlinear systems. They can be crazy but beautiful. To what extent do we have any right approximating it even locally as a linear system? So let's think about even the pendulum. Again, I'll mostly when I need to draw something, I'll use the pendulum. Okay. Let's think about balancing the pendulum around the upright, making a local linear approximation, right? So here, x is theta dot. U is just my tau. I'm going to linearize around theta equals pi, the upright, yeah? Theta dot equals 0, u equals 0. And that's going to be a fixed point, right? If I write my system out like this, then I can approximate that with f of x0, which is 0, plus my partial derivative, which is going to be a matrix, right? It's the element of this with respect to the first variable, here, then the element of the first row with respect to the second variable here, right? Okay, so this is partial f partial theta is 0, partial f partial theta dot is 1, partial f2 partial theta is just negative g over L cosine theta, right? And then I get a negative b over ml squared, and I'm going to evaluate that at theta equals pi in just a second. And then what is b here is just 0 over 1 over ml squared. Okay, so cosine of pi is negative 1. So I get just 0, 1, positive g over L, negative b over ml squared. X bar plus 0, 1 over ml squared. U bar. People okay with the mechanics of that? Totally fine to ask questions. Thought it'd be worth doing it once.
Is this the kind of thing we should know how to do for future purposes?
You won't have to, but it's, it makes you a better person, right? Yeah, I think that's the right answer. I think, it's, we have algorithms that'll do this for you in, in the software. Okay, so this is a little much. Let me insert some numbers, and here's something I tend to do in this class. I'm going to just set mass equal to 1. Let's set length equal to 1, whatever I can to make these equations easier. I'll say damping equals 0. I can't get myself to say gravity equals 1. I got to make that a 10. But that's still way easier than 9.81 or whatever. So my system here is A equals 0, 1, 10, 0. Yeah. And B is just 0 or 1. So the cool thing is, we already know how to plot phase portraits of systems like this. We didn't really do linear systems as much as we could, but it's worth doing here. So if I want to plot the phase portrait, x1 versus x2, which is equivalent to being theta versus theta dot here. For the system, I'll call it x1 and x2 because I like using this notation now. I've gone to the linear system. X equals ax. Okay, we'll draw it for u equals 0. Then how do I draw the phase portrait for this? And it's really, I'm doing this even in the error coordinates, right? To have my linear system. Well, the key to drawing the vector field here is to understand the eigenvectors and eigenvalues of A. Okay? So, right, so I'll just do it super quick. I want this, so I want the determinant of this equal to 0. If I pound that out, then I get the determinant of negative this, negative lambda equals 0, which gives me two eigenvalues. and corresponding eigenvectors, 1 square root of 10 negative 1 square root of 10. Okay. So what does this tell me about my vector field, my phase portrait? So first of all, for everything that's on V1, I know that the flow is just along V1. It's just a scalar times V1. So let me draw V1 here. It's kind of steep, right? So it's about 3, it's the slope is so it's 1 for square root of 10. This is the vector V1, okay? And for every point on the vector, I know that I'm just going to end up with my derivative pointing, positive times that vector. So I'm going to be, my vector is going to be like this, and in fact, everywhere along this, I'm going to be going out in the same direction as my vector. Okay? The other eigenvector where I know exactly what the phase portrait's going to look like, pretend that went through the, I'll fix that. This is V2, and again, whenever a point is on V2, I know that multiplying it by A is just going to give me a derivative that is also V2. This time, my eigenvalue is negative, so I'm going to be going towards the origin always. Okay, so this is because lambda is positive here, and this is because lambda is negative here. Now the beautiful thing about linear systems, especially linear systems whose eigenvectors span the space, is that you're basically done. Now you know what the whole vector field looks like, right? So I can write any new vector x as a linear combination, alpha 1 times v1 plus alpha 2 times v2, right? I can use that as a coordinate system, and then that means x dot for that is going to be alpha. It becomes easy to plot the vector field. So everything in between is a weighted combination of the effects that happen on the eigenvectors directly. So what does that mean is here I get a contribution from this and a contribution from this. And in fact, if you start plotting it out, it does this. And here, it's going to be dominated by this one here, but then as it comes here, it gets dominated by that one. So it does this, and then I get this over here, and I get this over here. Okay? So that's my linear system, which we got by taking a Taylor expansion of the pendulum dynamics. Is it any good? Is it useful? Right? So the trick here is that, I forgot my colored chalk, but if I were to zoom out a little bit, this is actually very familiar. There's an eyeball sitting here, right? And this one is here. Remember, we've changed coordinates around the upright, but in fact, it's like that. And over here, wouldn't you believe it's just like that? And it's just like this, right? So actually, it's really satisfying, at least in the vicinity of the fixed point. Yeah?
How do we know that it's an eyeball and not parabola?
This is the familiar pendulum. The linear system just radiates out exactly in the original pattern I was showing. There is nothing that's coming back in for the linear system. What I'm drawing now is the original nonlinear system on top, which I wish I had my different colored chalk to do that, I apologize. But if I put the original pendulum dynamics on top, then what we can see is that this linear approximation, it's smack on right here at the upright, which is what you'd expect. Like the the slope of which this orbit approaches that fixed point is captured by that eigenvector. Right? These curves are locally approximating the actual orbits around the pendulum, right? And even this sort of, I missed the upright and I'm spinning around, even that gets captured pretty nicely, okay? Of course, if I go all the way past the eyeball, for instance, then the linear system's still going to say this, but the nonlinear system's saying this, so there's a limit to how well it's going to work. And that's going to be part of our game here, is to understand, for what vicinity of the nonlinear system is the linear approximation valid? And that's a question we have good tools to answer, and we will, okay? The advantage, of course, of making that linear approximation is that we understand a lot more about linear optimal control than nonlinear optimal control. So once we get close to here, we can expect to have a solution that is pretty close to optimal for the nonlinear system by using that linear approximation. Yeah? Okay, so the way you do that, of course, then, is you take your A and B matrices from your linearization, and you could derive it by hand, or you can just call the methods we have available for you, right? So, in PyDrake, you do this. And you have to pass in A, B, Q, and R, which is my cost function, right? In fact, we also make it, you can also just call it this way. Since there's nothing hidden, there's nothing, calling a linear quadratic design principle, algorithm, against the nonlinear system implies that you're going to take a linearization. So we can also just pass in the system. You guys, I don't know if you've yet come to terms with this, the fact that we call this thing the context, and then QR, and it'll spit out a system like this, okay? So this is, the context is just a summary which has X and U, so it's capturing X naught and U naught. It also has parameters. It's everything you need to be able to run a simulation, okay? And you can just call it like this, and it'll linearize the system for you, and then call LQR and return even a system that you can use in a simulation that implements the linear feedback, right? And just to prove that this is a general thing, like in MATLAB, they have the same methods. It's, it looks like this. And, they don't have the concept of a system as, well, they do if you have the control system toolbox, but, yeah, and there's actually an analogy to this in the control system toolbox if you have a linear system. The linearization part they don't have, I guess, but you could. So, just to make that, I guess, show that in code here, so, are people sort of okay with this idea here? So this is how it looks in code, is that, for instance, if you want to stabilize an acrobat, you just make the acrobat. Again, there's a bunch of things that you have to keep track of to run a simulation, most of which are state and inputs. We lump those together into a context, okay? There's good reasons for that. Sorry if it's the simplest cases are more complicated for it. You can then set the state of the acrobat used named setters. You can just say theta 1 through whatever. You can set U to be 0. And then, for instance, you can call linearize directly on that and print out the AB matrices. Okay? So you get some big complicated matrices for the A and B. You agree that those are the right size at least, right? and that B is 0 is in the right place. Okay, and then the first question before you call LQR really, I mean, LQR is going to check this for you. You can ask, is it controllable? And we'll talk about that a little bit more in a second. Luckily it is, okay? And then you can just call LQR on it, and it'll tell you my feedback gain, all right? The output, of course, is two things. It's I didn't actually plot it there, but it's K, but it's also this S, which is my cost to go, which is going to give me that the contours of S are a cost to go that goes like this, and it similarly is going to capture the fact that it's cheaper to be here, where you can ride the dynamics into the origin, than to be here. So it's going to go up more quickly in this direction and more shallow in this direction. So it really does capture the long-term dynamics. So that's really awesome, actually. Like I think I want to make sure you appreciate what LQR is doing for you, and this is, I think, a tale that is worth telling, because we're going to have to, when we're trying other control design techniques, we're going to have to remember that this kind of thing happens. So the design here is that you're given A and B. The world gives you A and B once you have an operating point, a fixed point. You get to pick Q and R, right? But then you just call LQR and you get a controller back. And there might be some preference, might be some rules of thumb or whatever that you'll get better at picking Q and R to get different performance, okay? But that's a very convenient handle to be able to, sort of knob to be able to turn in order to have control of your system. What we care about, if we just care about whether the system is going to balance or not, what we care about is the closed loop stability of the system, right? So what you're doing is designing a K so that the closed loop system is stable, right? Alternative control approaches, design control approaches, you might think, oh, I'll just try to search for a K directly, right? It can be very hard to tune K directly. Okay, for instance, when we get into reinforcement learning, one of the standard approaches is a policy search, where you would, for instance, have the K as your parameters that you're searching over. You run an experiment, you change K a little bit, you run an experiment, you change K a little bit. Okay, but even in the linear systems case, it's not clear that that's a good idea. Okay? So, I mean, I can come up with a trivial example. If I make the following system, K1, if my closed loop system ends up being as simple as this, which could easily, I mean, simple choices of A and B would generate this, right? So how do I know that this thing's stable? I have to take its eigenvalues, and for a linear system, and you can see from the plot, you want all of the eigenvalues to be less than 0, right? That's the condition for stable linear systems. So if I try to compute the eigenvalues of this, I get -1 plus or minus, what do I get? This. If you plot that as a function of K1 and K2, there's a critical point where lambda equals 0, where there's at least one eigenvector that equals 0. This is the K1, K2 equals 1, I guess. Yeah. Curve, and here, okay? And actually, over here, you're stable. And over here, you're stable. Let alone, we haven't even talked about optimality. This is just, are you going to blow up or are you going to converge, right? Over here, you're stable. Okay, but everywhere else, you're actually unstable. This is just the curve of maximum eigenvalue equals 0, is this curve. Okay? So if your goal is to maximize some criteria of performance, and your strategy is to start guessing a k, and then move around and try to improve it, the best thing might be way over here, and you're going to have a hard time just kind of changing k a little bit and finding that solution. Right? So in general, even for linear feedback, the stabilizing controllers, this is an example, are certainly non-convex sets and even disconnected sets. Okay, so LQR is actually doing an amazing thing for you, right? If I had to just guess a K and hope it works, so on the Pendulum, you're going to be fine. On the Acrobat, it's pretty squirmy, okay? Good, I would wish you luck if you're trying to guess K for the Acrobat. But for Atlas, it's right out, right? LQR is this magic thing that says, if you give me, for any Q greater than 0, R greater than 0, it will return a stabilizing K. And the best K, up to your preference, right? The way you've chosen your cost. Right? So it's doing something very clever to reparameterize this potentially very ugly space. And it's hidden in the solution of that Riccati equation. So let's appreciate LQR. It's a good thing. It's an amazing thing, really. Now, there's an interesting thing that you could ask. Any interesting things to ask? You might ask, can I parameterize every stabilizing controller, right? So is it the case that if I wanted, any controller here, is there always a Q and R that I could pick to get that controller? And the answer is actually no. So, there are other parameterizations that people know about. The EULA parameters are something maybe we'll get to later. This is just a culture thing, it's not even, I didn't mean to say that today, but there's something called the EULA parameters, which is a different parameterization which actually parameterizes the entire class of stabilizing controllers. So, yeah. But LQR is great. It does magical things for you. For instance, so how should you pick Q and R? Even for the Pendulum, right? There are some sort of standard recipes for picking Q and R. For the Pendulum, I tend to pick, or you'll see even in the carpoles and Acrobats, you'll see that I will often do something like this. There's like these factors of 10 that pop up. Okay. Choosing it diagonal is just simpler to think about, and it's less numbers to assume, and that's often pretty good. And then you'll say like R equals 1, for instance, or for the Pendulum. Why would I tend to pick, why would you see a bunch of 10s lying around? Well, it turns out that these things live in different coordinate systems, or different, so this is in units of radians, this is in radians per second. This is multiplying my velocity term. And so I tend to try to scale out the units properly, by square root of G over L, if it works through. If you remember nothing else, you tend to have a 10-to-1 ratio and you're pretty good. It works almost always, because everything's about a meter, and gravity's always 10. So it kind of works out, okay? So if you see these 10-to-1s, that's where it comes from. There is some method to the madness. And what would you expect to see if I were to, let's say, change R and Q, right? So let's say I just take R and start ramping it up. Then what would you expect K to do, even for the pendulum? Would you expect K to go up or down in general? If R's the penalty on control action, then you'd expect it to use less control, smaller K's, as you crank up R, okay? But if you look for the pendulum and you do the experiment, as you crank R up to infinity, and really all that matters is the relative magnitude of R and Q, right? Because if I crank up Q at the same time, but if I hold Q fixed and I crank R up to infinity, K will asymptote, like K1 for the pendulum, the first element, asymptotes to 20, which turns out to be exactly what it would need to fight gravity. It'll never go past, it'll never let you make an unstable controller, okay? But it'll give up as much as it can. It's beautiful. It really does a lot of stuff, even though it's a linear control. So I should be clear. So I guess I've said before. So linearizing. Local linear approximations. I think are good, right? It's not the same as feedback linearization, of squishing my dynamics more globally because I have excessive control authority. This is I don't want to say it's always bad, but just to make a point, right? So this is a different idea. And I could make potentially lots of linear approximations and capture my dynamics in different ways, right? And I think because we know so much more about linear optimal control, this becomes a powerful idea. Questions? Yeah?
Could you apply LQR to the pendulum and make it switch which K is using as a reverser stasis?
So,
is that practical in real life?
You have to be careful. What a lot of, you'll hear, if you might have heard of gain scheduled linear control, for instance, it's a common thing to do on a fighter jet, for instance, is that you'll linearize around multiple operating regimes and switch between them. You have to guard against the fact that you don't want to switch the dynamics too much. So some care is required, but there is theory for that. Building on the success of linear control, that's sort of the next rung out is a bunch of linear approximations sitting on top of each other. Yeah?
Just a high-level question to make sure I remember things correctly. So LQR is just is the linear continuous version of value iteration, and then value iteration just works for non-linear things.
So let's use the words dynamic programming, because dynamic programming to computer scientists might mean the algorithm, but it also means it's what we've been calling the equations. The optimal control conditions come out of dynamic programming. Value iteration is the numerical algorithm we use to do dynamic programming on a discrete approximation. In particular, I tend to use value iteration for the infinite horizon case. And then LQR is an analytical solution to dynamic programming that works if you have linear systems. Yeah? No, it's great. Yes?
Could you re-explain the condition of eigenvalues to make systems stable?
Oh, good. So we saw that along an eigenvector, things move out x dot equals ax equals lambda times v. So along an eigenvector, I just get lambda times v, which means that if lambda is positive, I'm moving this way. If lambda is negative, I'm moving this way. And similarly, wherever I am, I'm either moving towards the origin or away from the origin. So the condition for stability requires that all eigenvalues are less than 0. Less than or equal to 0 if you want marginal stability, strictly less than 0 if you want convergence. Yeah? So I will often, like the plot I made is sometimes you'll plot just the maximum eigenvalue. And if that's less than 0, then you're good. Okay, so another important idea, since we got the linearization up, is that you can ask about controllability. Oh, sorry, go ahead.
So why is feedback linearization worse than local linear approximation?
I'm saying that a little bit tongue-in-cheek. I'm trying to just to make a point. Okay, so when you're in here and the dynamics are almost linear, then you should use them and treat and think about them as a linear system to the extent that it affects it. But what I want you to do is use the real dynamics. What I don't want you to do, feedback linearization, is applying a control to erase the board and make it linear everywhere. And I'm saying keep the board, and it's okay to reason about it in chunks, because that's what we know how to do better. Just don't erase the board and replace it. And in fact, for underactuated systems, you can't. So so this stability question is just a function of a closed loop system. It doesn't say anything about if you have control input. A related question is controllability, which says if I have A and B, you can ask, is that pair A and B controllable? Which means, does there exist a sequence of control inputs that would take me from any initial condition back to the origin? And for linear systems, actually, that's a question you can ask efficiently. And if you've grown up with this stuff, you know the answers to that. There's a simple condition, and you can just ask, is controllable of a linear system in any standard software package? Okay. But the interesting thing is, so controllability. Let me write it down because it's. Someone actually asked this after the first lecture, which is a good question. You might think that controllability and underactuated are the same thing. They're not, right? Controllability is that for any initial x, controllable if a system is controllable if for all x 0, there exists some trajectory u for which x at time, at some capital time. Let me actually be a little bit more careful here. There exists a u of t with t in some finite interval for which x tf equals 0. At least for linear systems, just asking, can you always get back to the origin is sufficient to talk about controllability, because you can always map that anywhere. For nonlinear systems, you might want to ask, can you go from any state? Controllability means from any state to any other state. Okay? The acrobat, for instance, is underactuated. You can't go in arbitrary directions, but it's controllable. In fact, most of the interesting systems is, if it's not controllable, it's less good for deploying as a robotic solution. okay? So underactuated and controllability are different. Okay, so let me show you that this stuff really works. So I wanted to plot out in this window just that that it's easy to write the code, okay? But then if we actually go and run the code here, so I'll do the cart pull first, exactly the same math works, and I'm stabilizing the origin, which is somewhere around here, and again, I'm going to give it a push at the beginning of every, at every 10 seconds or whatever it is, and it's going to try to recover, okay? Now the cart pull is actually relatively easy to control in the sense that the linear feedback does well for a large portion of the state space. So if I plot that vector field, it actually works for a big part of the state space. The acrobat is a little bit more squirmy. Same code, except you call acrobat instead of cart pull at the beginning. And I'm going to start small initial conditions away from the top, but this time your mileage may vary. I mean, it's pretty small initial conditions, really. And sometimes, there are known states for which it's guaranteed to work, but there are other states that are pretty close to upright for which it's going to wipe out, right? And actually getting that hardware acrobat to work, it was like the dragon we needed to slay in lab for a number of years. It took a really long time to really make that work well. And even when you wanted to, if you watch it again, to the top. It is so hard to get rid of that last little oscillation. And you guess what?
It's like slipping everything.
There's stiction, right? It's friction, right? So we actually built a special drive. It's a direct drive with a slip ring, basically, that's trying to be a friction drive to try to maximize our chances, reduce backlash, okay? But still, you get to the top, and if you're exactly at the top, you're done. You just do nothing, and you're good. If you're just a little bit off, then the controller says, give me a little bit of torque. But that little bit of torque isn't enough to overcome friction. You got to go a little bit further, and now I got enough torque, but then I overshoot. And it's very, very hard to get around that, right? Very hard. So that's as close as we ever got, partly because we were kind of done trying, honestly. But it's hard, and it's very hard to do that. Okay, exactly the same stuff is going to work for quad rotors. So this is my Python drawing of a quad rotor, which you'll be able to play with. This is the planar quad rotor. Okay. So again, now I've got a fixed point that is, U is not 0, because I have to have, my nominal operating point is applying some thrust going upwards, otherwise I'll fall down. But if I just take the equations of motion of that system, linearize it around the top, call LQR, you're done. And actually that's why quad rotors are great. I really think that is why quad rotors took off, is because you write a tight enough little control loop, then control suddenly becomes easy. And they have enough control authority that the linear control works very well over a large regime. Okay, when you start getting into higher angles of, faster speeds, then you get some more nonlinear effects. You get like a lift. At some point, so I used to joke. I guess I've lost. So I used to be like the fixed wing guy trying to tell the quad rotor guys they're silly, and I clearly lost. The quad rotors have won. Maybe in 10 years people will use fixed wings again, but quad rotors are stupidly inefficient, right? There's this great idea called the wing, which produces lift as a reward for moving forward, and quad rotors don't actually have them until you move forward fast enough and that your props start looking like a wing, and then it screws up your equations a little bit, which is where the linear control starts breaking down. And so the name of the game here in quad rotors is that you can do almost anything in a lab pretty well with linear control. And it's only when you start getting into the really high gusts of wind outside or really fast motions or ground effect where the nonlinear terms start coming in and the linear control stops working as well. Okay? If you had itty-bitty motors, then you might also need more nonlinear control because the saturations could come in and affect things. But quad rotors, the other thing that happened with quad rotors is people got outrunner motors, right? So there was a revolution in hobby motors that gave you just way more prop thrust per weight, and that changed a lot of things. Okay, and so, and I don't want to give you the impression that this only works for cartoons. Oh, this isn't, what I'm about to do is not much better, but so here's just a little 3D visualizer, which is that. Let me do the quad rotor. TAM complete got me. Okay. Oops, sorry, it's compiling, but it'll run in a second. That's faith. See, I used to not be in a place where I would just know that I pulled master and it would just definitely work. But I guess I should not say that to myself and then jinx myself. I can't make MacBooks faster. That's one thing I can't do, but there we go. Okay, so here's a little quad rotor. This is now the full 3D dynamics of the quad rotor. Same thing. And actually, I mean, it stabilizes from a long way away. Even though it's got reasonable torque limits, it can almost turn itself from upside down back up to upright. Right? Quad rotors are sort of easy in that sense. Okay, it's probably horribly distracting, so I will stop that. All right, so this really works, and there's just general recipes that I think are useful to know. So for instance, if you take the manipulator equations, which I've lost at this point, I think a lot of the work we end up doing in this field, I guess, you can write an optimization or a numerical recipe assuming that x dot equals f of x. But whenever you can take advantage of the fact that there's more structure inside that equation, then you're going to be able to write more sophisticated algorithms. And we're going to see that over and over again. And maybe just the first simple way to see that is even linearizing the manipulator equations. It turns out that if your system is at a fixed point, then a lot of these terms disappear right out. I don't even actually have to evaluate M. I don't have to evaluate C, right? So I really am just looking at the equilibrium conditions, which is fighting gravity. And you have like so much less work to do. And it works out to basically be your A matrix is as simple as, I guess you do need M eventually because it contributes to this term, but it's, the whole thing works down to just be a few terms. You do get a dependence on C here. I guess I spoke a little bit too soon. Most of the terms actually do drop out. Okay. So if you were to linearize this whole equation, you'd be doing a lot more work than you would need to do. There's a special form once you know that that's structured equation and that this has to be a fixed point. A lot of terms are just naturally zero, including some of the ones that are less fun to compute. Okay? Now, an important question that we're going to get to very soon is this idea of when does my linear control work for the nonlinear system? Okay? So in these plots that I've been making, there's a question that I'm just going to set up now and we'll talk about next time here, which is, can I identify a subset of this state space? For instance, maybe it's a sublevel set of J. Like a contract that I might like to have is that if my cost to go is less than some number, which means I'm inside one of these rings of the contour plot, then I'm guaranteed that the nonlinear system using the linear controller is stable. Okay? You can imagine that if I could give you that sort of a certificate, then you could start applying this in various parts of the state space. What happens if I try to linearize about here, though? Can I linearize around that point? The thing I said before was no, because f of x0 u0 here does not equal 0. So linearizing around this, if you picked this point to linearize about and made a coordinate system that stayed there, then what you would get is a system that was affine in control. It would have some extra term in it. And actually, it's more work to stabilize those systems. It's not even clear it makes sense. It depends on what you have going on. Okay. But we're going to talk about ways where you can have a moving coordinate system that follows the orbit of the original system and try to linearize along a moving coordinate system. Okay. But this sort of next component is to understand when the linear optimal control works for nonlinear systems. And that'll give us more tools. Any questions? Yeah?
What's the term for that idea?
So the thing we're trying to compute is a region of attraction of the linear controller for the nonlinear system. And we'll use our Lyapunov ideas, and we'll make algorithms that try to find Lyapunov functions to prove, just like we did in the original definitions. Yeah? Yes?
And you'd only make one LQR for a given system, just around a given fixed or stable point? You wouldn't have like multiple LQRs?
So I sort of gave it away with the title of that one video. It said LQR trees. So in fact, what we're going to end up doing, one algorithm that's out there is to actually make a network of LQR controllers, some of them that move along the trajectories that try to come in here, and some of them that just cover fixed points, so that you can eventually cover the entire space with linear optimal control. And if you have the two components of knowing how to design the linear controller and then being able to check rigorously when it works for the nonlinear system, then you can patch things together. Okay? All right, we'll see you on Tuesday.